In this video, I'd like to look at our equations for radioactivity, in particular equation 47. 45 and 47 are similar equations. They will solve for the same variables. They just look a little differently, but they are virtually the same thing. I'm going to stay with equation 47 right now, and here it is. Equation 47. N represents the final quantity of radioactive substance. Left after a time t. That time t is this time t here. So N represents the final quantity of radioactive material that is left over after a specific time. The units for quantity is going to be in milligrams or in kilograms, or we can use grams or even micrograms, some unit of mass. N naught. This is pronounced N naught. Also written N-A-U-G-H-T. The zero here is an old English term meaning zero, naught. This is pronounced N naught. N naught then is the initial quantity. And again, being the initial quantity, this being the final quantity, it has units of milligrams or kilograms or grams or micrograms or any other unit of mass. Let's look at lambda. This is known as the decay constant. Lambda can be found by using the simple equation. Lambda is equal to ln of 2 divided by the half-life of that particular species. Every radioactive element has its own separate half-life. Therefore, it also has its own value of lambda. Sometimes this is shortened. The ln of 2 is 0.693, etc. Sometimes this is simply shortened to 0.693 divided by the half-life. I'd prefer to use ln 2 and just use all of the values of ln 2 in the calculator. And since this is in time, the units are going to be in seconds or hours or days or years. And it'd be in the denominator, so it's per second, per hour, per day, per year. Seconds, hours, days, years. For the time portion, that's a constant. This is where the time is. And lastly, we have time. Little t stands for time, and time is going to be in seconds or hours or days or years. Whatever value of time we're using here needs to be used here as well in order for the two to cancel out. So if we use seconds for lambda, then seconds must be used for the time here. If we're using days for lambda, then this one must also be in days. Looking at E, I'm going to bring it down here. E is known as the exponential constant. Exponential constant, also known as Euler's number. Euler was the mathematician who discovered the value of E. And E is a number. If you look at your calculator for the value of e to the power of x, there we go. Turn this on. To find the value of e, just make x equal to 1. I'm going to bring up x. Second function, e to the power of x. That's this one here. There it is there. And if I place a 1 where the x will be, 1, press the equal sign, that is the value of e. It is similar to pi. Pi, 3.14176, etc., etc. And e then is 2.718281, and so on. So instead of using this number, we use the letter e, the exponential constant, e. If I were to say e to the minus x, this has a name known as the exponential decay. And that's exactly what we have here, e to a power of minus x. In our equation, e to the power of minus, this will be the x value right here. So it's an exponential decay. If I were to graph an exponential decay, it would look like this. And you will see this graph here in some other literature that I have posted.